All right, everybody, welcome to the video here for lesson number 5. So in today's lesson, we're kind of putting everything together. So we learned a little bit about arithmetic sequences, geometric sequences, and recursive sequences. So we're just able to essentially look at everything here all together. So the opening exercise is kind of just a review of everything we've done so far. So some of the types of patterns. The first pattern is arithmetic, right? These have a common difference. All right, so when I get from one term to the next, I'm using addition or subtraction. So I'll put addition or subtraction. A geometric sequence has a common ratio, meaning to get from one term to the next, we're either going to multiply or divide. So we have multiplication or division. There are ways of writing each type of sequence. So an explicitly defined sequence for arithmetic is going to be a sub n is equal to a sub 1 plus d times n minus 1. To show that same sequence recursively, I'd have to state the first term and then state some rule. So the next term is equal to the previous term plus the common difference. This is an arithmetic sequence. A geometric sequence, we'd say explicitly defined would be the first term times the common ratio to the n minus 1. To show that recursively, I'd state the first term, and then I'd say any term of the sequence is equal to the previous term times the common ratio. The difference between explicitly and recursively defined sequences is just us showing it differently. That's all it really is. Okay. The big thing about recursively defined sequences is just understanding how they work. So let's take a look at number 1. So it says, write an explicit formula for a sub n, the nth term of the recursively defined sequence below. So what this is telling us, it's telling us the first term, right? This is the first term. And it's telling you that it's geometric because it's a product. And we're saying multiply x to each term to get the next term. That's what this is saying. Remember, this on this side, no matter what it is always the next term. So if I wanted to write a explicit formula, I'd say a sub n is equal to the first term, x plus 1, times the common ratio to the n minus 1. Well, the common ratio is just x. The reason why the common ratio is x, because that's what we're multiplying each time to get from one term to the next. So then it says, for what values of x would a sub n be 0? So if I say this is equal to 0, I have x plus 1 times x to the n minus 1. So x is equal to negative 1. That would make this 0. X also can equal 0 because that would make this 0. 0 to any exponent would be 0. This is kind of a strange question, but something that works, right? A big part of this question is just understanding how the sequence works or the pattern works. So for each of the questions on the next page, what we're asking you to do is determine, is it arithmetic or geometric? State the common difference or common ratio if there is one. Write an explicit formula, and write a recursively defined formula. So the first one is arithmetic. The common difference to get from negative 6 to negative 10 to negative 4, each time I'm going down by negative 4. So the explicit formula would be a sub n is equal to the first term minus the common difference, since it's going down instead of up, I'll use a subtraction, times n minus 1. This would be the explicit formula. The recursive formula, I would have to first state the first term. and then state how we get from one term to the next. So the next term is equal to the previous term minus 4. Let's try another one. The next one is not a arithmetic sequence. I noticed that the difference here each time is different. But if I look, the common ratio is something that I can figure out either by mental math by saying that each time each number is getting cut in half, or by saying, well, since it's geometric, I know the common ratio is equal to the second term divided by the first term. So the common ratio here is 1/2. So the explicit formula would be a sub n is equal to the first term times the ratio to the n minus 1. The recursive sequence, I'd state the first term, and then I would go through and say, well, the next term is equal to the previous term times 1/2. So here's a time where I'm going to ask you to pause the video. So take a minute, pause the video, and try the next two. One of them is geometric, one of them is arithmetic. So go ahead, pause the video, and then come back and check your work. All right, welcome back to the video. So as you can see, I did the last two here for you. So if you just take a moment here to go through and check your work. So for the first one, I noticed that it was geometric. One of the things we said in the geometric lesson was if you see that your sequence goes from positive to negative, only a geometric sequence can really do that. So we kind of knew that right away. To find the common ratio, I divided the second term by the first term, which gave me -3. I then wrote the explicit formula and the recursive formula for each. Second one there was arithmetic. I noticed it had a common difference. Common difference was 11. So I wrote my explicit and my recursive sequence there. Hopefully you got these two right. If you didn't, just take a look and try and figure out where you made your mistake. And then let's go on. So one of the interesting things about sequences is if a sequence is arithmetic, I can always find a missing term. But if it's geometric, I can also always find a missing term. Now, some sequences might have the same 6th and 8th term, and one being arithmetic and one being geometric. So one of the things that they can do is they can give you two terms of a sequence. Doesn't have to be the 6th and 8th term. It could be the 4th and 9th term. And they can say, what is one of the terms of the sequence if it's arithmetic or if it's geometric? And the answer is going to be different because in an arithmetic sequence, to get from one term to the next, you're using a common difference. In a geometric sequence, you're going to use a common ratio. So let's start with the arithmetic part because that's the easier part. So I'm giving you the 6th term. So I'm giving you a sub 6 is 36. I'm not giving you the 7th term. And I'm giving you the 8th term is 64. So to get from 36 to 64, I can say the difference between those two, 64 minus 36, well, that number, 64 minus 36, is 28. So I'm adding 28 to get from 36 to 64. Well, I want to take that 28 and I want to split it into two evenly sized pieces because the difference here between the 6th and 8th term is 2 terms. So if I take 28 and divide it by 4, I get 14. That's my common difference. So to get the 7th term, I'd say 36 plus 14, which would be 50. So the 7th term of this sequence would be 50. Now it works because if I add 14 again, I would get to 64. So I found the common ratio, the common difference there, just by playing essentially with the numbers. Now things change a little bit when we're talking about a geometric sequence. So if I know the 6th term is 36, 7th term I don't know, and the 8th term is 64, to get from 36 to 64, I want to figure out what multiplies by 36 to get all the way to 64. So to do that, I'm going to divide 64 by 36. So 64 divided by 36 is a decimal. It's not a nice decimal, so let's change it to a fraction, 16/9. Now, instead of saying I want something that adds twice to itself, I want to figure out something that multiplies twice to itself to make 16 over 9. Well, when we're thinking about that, we're saying, well, what's the square root of 16 over 9? That would figure out what multiplies to itself to make 16 over 9, and that answer would be 4/3. So the common ratio is 4/3. So if I take 36 times 4/3, I get 48 for my middle number. So a sub 7 could be 48. Or a sub 7 could also be negative 48. Now, this wouldn't happen in an arithmetic sequence, but in a geometric sequence, this seventh term could be negative. Because if your sequence goes in the pattern of positive, negative, the sixth and eighth term could potentially be positive, and the seventh term could then be negative, and it would still fit in your sequence. Meaning this common ratio could also be negative 4/3. Hopefully that makes sense. If you're a little bit confused about that, just go back here a page and look at this sequence. See how it goes from positive to negative? So if I gave you the second term and the fourth term, and I said find the third term of this sequence, it could be either 36 or negative 36, depending on the type of ratio that we have. Okay? Let's keep going. Number 4 says Kristen wants to increase her running endurance. According to experts, a gradual mileage increase of 10% per week can reduce the risk of injury. If Kristen runs 8 miles in week 1, write a recursively defined sequence and an explicitly defined sequence to represent the number of miles she would run in the nth week. So to increase by 10%, the common ratio is going to be 1.1. I need the 1 there to increase the value, okay? Remember, it's always 1 plus the percent is equal to the common ratio. So if I wanted to write a recursively defined sequence, I'd state the first term, which is 8, and I'd say any time of the term of the sequence is equal to the nth term plus, or not plus, times 1.1. There's your recursively defined sequence. An explicitly defined sequence, you'd say any term of the sequence is equal to the first term times that common ratio to the n minus 1, where I can plug in any term there of that sequence. Number 5 talks about a stadium. It tells us that a stadium has 300 seats, and each row thereafter has 14 more seats. So the first row is 300 seats. And then the second row would be 314 seats, and then the third row would be 328 seats, etc. So we can see that this is defining an arithmetic pattern or arithmetic sequence. It says to recursively define the sequence. So to recursively define this, I'd state the first term. I'd say any term of the sequence is equal to the previous term plus 14. To do this explicitly defined, I'd say, well, the first term of the sequence plus the common difference times n minus 1. So here's your recursive. Here is your explicit. One of the big things about this lesson is understanding that these are actually generating the same exact sequence. They just look very different, and understanding what's different about them. All right, so at this point, I'd ask you to pause the video or come back to the video and try your homework assignment. Remember, you should be trying the homework before you actually watch the video. All right, see how you're doing on it, and then come back to me. All right, so welcome back. Let's see how you did on the homework assignment. So for the first question here, that first sequence that we see is an arithmetic sequence. So to write a recursively defined rule, we'd state the first term. We would then say any term of the sequence is the previous term plus the common difference, which is 6.5. To do this explicitly, we'd say any term of the sequence is equal to the first term plus the common difference times n minus 1. Next one, we notice that this is a geometric sequence. Common ratio in this case, if I take 100 and divide by 80, we get 1.25. So to show this recursively, first term is 80. You have to say the first term in a recursive sequence. Then any term of the sequence times 1.25. To show this explicitly, we'd say any term of the sequence, first term, times the ratio to the n minus 1. Okay, number 2. A sequence is defined by the rule a sub 1 is 8, so the first term is 8. And then a rule there that says any term of the sequence is equal to 3/4 of the previous term. So we know the common ratio. We know the first term. So we can actually write this rule. We can say the explicit rule is the first term times the common ratio to the n minus 1. So even though I didn't know more than just the first term of the sequence, just by knowing the common ratio, I'm able to write that explicit rule. Number 3 talks about Jenny. Jenny planted a sunflower seedling that started out at 5 centimeters tall, and she finds the average daily growth rate is 3.5 centimeters. So each time that this sunflower is another day old, it's going up by 3.5. This makes it an arithmetic sequence. This is the common difference. So to write a recursive rule, we'd say the first term is 5, and then any term of the sequence is equal to the previous term plus 3.5. Number 4 says a bouncy ball rebounds to 90% of its original height preceding each bounce. Craig drops a bouncy ball from 20 feet. Find a recursive rule for the height of the ball. So this one, to find the common ratio, so we're starting at 20 feet. And if I take 20 times 0.9, I'd be at 18 feet. So that's 90% of the previous. What did I multiply here? I multiplied by 0.9. So the common ratio is 0.9. So recursive rule here would be the first term is 20. To get to the next term, I'd say the previous term times 0.9. And that's it. Hopefully this video helped. As you are going through and trying these videos, make sure you email me if you do have questions, and hopefully I see you soon.